How does the PV diagram of a simple two-stroke engine relate to its full cycle of operation? So I'd like to compare the diagram I've drawn in PV space to what a real engine looks like. And I have some pictures here in the slides that are going to help us achieve that. So this is a two-stroke engine simplified. I have some of the necessary components there, but a lot of mechanical details are going to be left out. We're starting at what is labeled in the PV diagram at point 4, and we're going to see what needs to happen really in the engine to get us ready for it to go up to 1, and then it'll go from 1 to 2 to 3 and then back to 4 to show a full cycle. So right now this cylinder is ready to receive some fuel, so some fuel comes in, it really quickly spreads out, and then the spark plug at the bottom there is going to ignite that fuel, and all of that's going to happen, and we're still at 4 on the diagram because no real changes in pressure and volume have happened yet. But once that fuel ignites, very quickly the pressure increases so quickly, because in reality really the engine is going to be moving in kind of a continuous operation. So I've shown a whole bunch of steps with the engine just sitting there. That's not entirely realistic, but what is realistic is this pressure increase happens very, very suddenly. So in the graph, the vertical line from 4 to 1 represents huge pressure increase with no real appreciable change in volume, and that tends to hold true for real engines, at least to a really good level of approximation. And then from 1 to 2, that represents expansion of this engine. That's really the power stroke. That's where most of the output work that is desired is going to happen there. The engine is doing positive work to the environment while it is still at relatively high pressure, but since it's expanding, that pressure does go down. So if you look at the graph, it's kind of a curve that starts out at a higher pressure, is heading towards higher volumes because it's going to the right, but as it does so, its height on the vertical axis is going down from 1 to 2, representing that loss of pressure. Now, at some point, usually in these graphs, as I kind of sketched on the whiteboard earlier, there's a kink, and that kink corresponds to when the exhaust valve opens. That's going to reduce the pressure even faster as the cylinder continues to expand. So that takes us from 2 to 3. And at that point, pretty much all the useful work has been done, but now we need to have some work done back to the system to return it so that it can do another cycle. Now, in reality, the engine is going to be connected to a shaft that's probably going to have a flywheel on it. There's going to be angular momentum there. And so if you ask, like, well, how is work done back to the engine? Well, since that angular momentum is there, that wants to kind of keep going, and it turns out in this part of the cycle, that's going to actually do work back to the engine, or really to the cylinder, and return it to its original state. But a bunch of things need to happen here because all the exhaust has left with air carrying like burnt fuel or expended fuel, and now we got to let some air back in. So the valves need to be carefully timed to make all that happen at the correct time. And now we're back to 4 where we kind of started, and then fuel can be put back in, and at that point we're ready to have the spark plugs ignited all again and keep doing this over and over and over again super fast. So even though there's negative work output at the bottom, because it's at higher pressure for the positive out work, each cycle you're getting net positive work output. And so if you do the cycles really, really fast, now you have a useful engine.